Many calcareous nanofossils are composed of R units, meaning, as we saw in the previous video, that crystallits have their optical axis in a radial arrangement relative to the direction of propagation of light, which, as you know, travels vertically along the microscope until it reaches our eyes or a digital sensor. But many others have a more complex arrangement with a combination of both R and V units. V units means crystallits of calcite in which the optical axis is vertical, that is, in the same direction as light propagates. There are also some calcareous nanofossils exclusively composed of these V units. What happens in these cases? As you probably already guessed, if light propagates along the direction of the optical axis of calcite, here represented as a blue dot, it vibrates in the equatorial isotropic plane of its optical indicatrix, and so it does not subdivide or suffer any rotation. In these conditions, the polarized light that passes through the polarizer is blocked by the analyzer and all the V units get extinct, independent of their orientation relative to the polarizer or analyzer. This is characterized as permanently extinct, since the behavior is similar to any other isotropic substance under cross-polars or cross-nickels, independently of how we rotate the stage. Here we have a case in which all crystals of this radial stellate calcareous nanofossil of the genus Discoaster are V units. In these circumstances, the microfossil is better seen in parallel polars or parallel nickels because when you change to cross polars, it disappears. Well, not completely. It might leave a ghostly profile that reveals its presence. This is why we are almost constantly inserting and removing the analyzer when we are screening calcareous nanofossil assemblages, for instance, in a smear slide. And what about those that have both R and V units? That's the case of this taxon, Coccolithus pelagicus sensulatum, here reconstructed in a silicon replica. Its structure is what is called a placolith, in which there are two series of crystallits arranged in a proximal and distal shields united by an inner tube. The proximal, this means closer to the cell, as you can see here in this reconstruction of its cocosphere, is smaller and is composed of R units. The distal is larger and is composed of V units. Taking in consideration what we said before, only the smaller proximal shield will be visible, and a part of the crystals of the tube can also be seen. This results in an effect that the placolith looks larger in parallel light or parallel polars than in cross polars, as we can see here. And what about the colors we see on calcareous nanofossils under cross polars? Are they the real colors of the crystals? No, they're not. The real color of a crystal can only be observed using parallel polars, which mean only with the polarizer inserted. Normally, calcareous nanofossils have whitish colors, but sometimes, especially if they are very thick or recrystallized, they can be yellow, orange, red, or even blue, like in this element of an ascidian spicule. Ascidians are benthic colonies of very small animals that inhabit shallow coastal environments, from which come most of my samples, but you probably will not see them much if you study open marine deep ocean samples. You'll remember that we have already mentioned that these spicules are made of aragonite, a polymorph of calcium carbonate distinct from calcite, but for this purpose behave both the same way. These colors result of the interference between the extraordinary and ordinary rays that emerge from the crystal. They are very useful and make petrographic observations sometimes really amazing. To understand how this interference happens, we need first to introduce the concept of retardation. As we mentioned before, in calcite, the ordinary ray travels slower than the extraordinary ray, meaning that when the two leave the crystal, there is a delay between the two. This is what is called the retardation. It can be calculated as the product of birefringence by the thickness of the crystal. We saw earlier how birefringence expresses itself. But how is it calculated? Birefringence varies according to the orientation of the crystal, but its maximum value is calculated as the subtraction between the two refractive indexes, Ne and No. For calcite, this is equal to minus 0.172. It's a negative value because Ne is smaller than No. And this is why we say that the optical signal of calcite is negative. We'll return to this later. Note that for calculating a retardation, we use the absolute value of birefringence. It is the delay between the extraordinary and the ordinary rays that is important, not who is higher than who. The retardation colors under cross polars are described in the so-called Michel-Levy retardation color chart, like this one. It looks like a series of rainbows, more or less repeating the same basic color sequence in several orders. However, note that they are not produced the way rainbows are. Rainbows are produced by refraction and dispersion of light inside the isotropic small water droplets, while retardation colors are produced inside an anisotropic mineral by double refraction and interference under cross polars. If these concepts don't make much sense to you, please return to the previous two videos. Here, the distinct mineral birefringences are plotted as lines. This is calcite's birefringence line. As we mentioned earlier, the retardation colors also depend on the thickness of the crystal. The thickness of the crystal is plotted on the left axis of this chart. The thickest the crystal is, the highest is the time difference of arrival between the faster calcite's extraordinary ray and the slower calcite's ordinary ray, and so the highest is retardation. The most common retardation color, here on we'll just refer it as color, of our calcareous nanofossils are the first order white. Due to the high value of the birefringence of calcite, this color is obtained with very small and thin crystals, less than 2 microns thick. Yellow colors indicate thicker crystals that may attain 2 to 3 microns. Orange-red up to 4 and blue up to 5 microns. So, these retardation colors indicate thicker elements of the calcareous nanofossil, like in these examples of Pontosphaera, or the occurrence of recrystallization, like in these Cretaceous specimens. This is also very important to register because recrystallization can hamper calcareous nanofossils identification. As we mentioned, retardation colors change very fast in calcite or aragonite crystals because of its high absolute birefringence, and that's why we can see several of these colors mixed together in specimens. This means that its thickness changes, like this element of ascidian spicule, thinner in the borders with whites of first order, and then towards the central part of the element gradually attains blues of second order, which indicate a higher degree of retardation between the extraordinary and the ordinary rays. Since birefringence doesn't change for this specific orientation of the crystal, this has to do with the rays traveling a longer distance inside the crystal, meaning that it's thicker in its central area. Since colors change gradually, this means that thickness varies gradually as well, giving us a perspective of the third dimension. The element is round in its equatorial plane.